Hi, everyone. Thank you for hurrying a little bit to your seats. We're going to start the next session. Guys, come on. All right, we're going to start the next session. Just a point of organization. At the end of this session, you're welcome to go ahead to the building where we had lunch. We'll have drinks, and then dinner will be served. So just, follow people who know where to go, or if you remember where lunch was. If you signed up for dinner. And that includes the locals. Okay. There you go. And then who's chairing this next session? You are. Great.
I'm not sure.
Perfect. There you go.
You are.
Okay. All right. Thanks. So this is our last session of the day on all things BSM physics. So we're going to start with Peter Graham. Okay. Take it away.
All right. Great. Thank you. It's really been a pleasure to kind of get a window into this community that I'm really an outsider of. I don't really know why I'm speaking exactly, but I blame Dan. Okay, I was asked to give kind of an overview of physics beyond the standard model, particle physics. That's obviously not possible. It's, a huge field of thousands of people working for many years. So the real title should be some random, personally, my own biased thoughts on things that I think are exciting now in particle physics and physics beyond the standard model. And I don't have specific things to relate to spectroscopic surveys, although I will try to throw out maybe at least a few hopefully interesting possibilities, and I'd love to maybe stimulate some discussion. So if something I say gives you some idea, I'd love to chat about it afterwards. But that's my my beginning apology. Okay. So why go beyond? Also, can everyone hear me if I speak without the mic? Is that good in the back? All right. Oh, the Zoom or something? Okay, sorry. Okay, I'll try to speak with a mic. All right. Okay, so why go beyond the standard model? Standard model, of course, remarkably successful, but I would say the tremendous success in explaining like all the lab experiments we've done really only deepens some of the very clear questions we still have. So for example, of course, what is the microphysical nature of dark matter? We know for sure it's not explained. We need something beyond the standard model, right? Also, the hierarchy problem, a major piece of motivation. This question, why is the mass of the Higgs, or really all the scales of the standard model, so far below what we think are the high fundamental scales in nature? It looks very finely tuned. We really don't know. That remains a deep, outstanding mystery. And in fact, our continued failure to find anything to explain it makes it even more of a mystery, I would say. Similarly, we have several other fine-tuning problems. So while dark matter proves for sure that there has to be physics beyond the standard model, we have several of these fine-tuning problems that we think, or we hope, give us some hints for what the physics beyond the standard model may be. So there's also the strong CP problem, which is the question of, if you like, the observable is, why is the nucleon electric dipole moment so small, so much smaller than we would have guessed if we just wrote down sort of generic order 1 operators in the standard model? Or also similarly, maybe the biggest fine-tuning problem, the cosmological constant problem. Why is that so much smaller than we would have thought the value it should have from its quantum corrections? Of course, there's lots of other really important problems too. How did baryogenesis happen? What is the mechanism for inflation and reheating? What creates these funny patterns we see in the fermion masses and mixings in the standard model? What is the high energy theory of quantum gravity? I'm just going to focus on these first 4 problems because already I can't even possibly do justice to giving an overview of those. But I just try to cherry pick a few maybe interesting examples. And mainly, actually, I wanted to focus on dark matter. So we know dark matter is something new beyond the standard model. What is it? What do we know? Well, we know very little about it. It's presumably some new particle, but we have no idea what its mass is within this, tremendously broad range here. We do know the mass of at least the dominant form of dark matter is at least 10 to the minus 22 eV, but it could be all the way up to the Planck scale and even beyond. If it's beyond, it's presumably any fundamental particle with a mass beyond the Planck scale, probably actually just a black hole, but it could either be black holes or it could even be, lumps, accumulations of fundamental particles. Of course, we have some guesses or some sort of well-motivated possibilities. So of course, for a long time, we focused on the possibility of something new with the weak scale. The WIMP is well-motivated both by having a natural dark matter production mechanism. naturally, satisfies all the constraints to be dark matter. You can get the right amount of it, and also is motivated by things like the hierarchy problem. So I'd say that's kind of the criteria we look for to decide when is a theory really interesting. If it's both natural, when is a dark matter candidate really interesting? If it's both, sort of naturally get the right production mechanism, the right abundance, roughly, the right properties, but also maybe associated to some other one of these big problems like the hierarchy problem. I think maybe the other kind of classic example would be the QCD axion, which both has a, again, natural production mechanism and can be the solution to the strong CP problem. And I think together, WIMPs and axions are probably, most theorists would agree, two of our best motivated candidates for dark matter. So I would, maybe give sort of more of my accumulation of prior probability in those spots on the mass axis there. But actually, I really think we should look everywhere. I think that this whole broad range of dark matter is incredibly interesting. It's really broad, so that's a huge challenge for us. I think that's one of the main things that's driving a lot of the work in BSM physics now. But the whole parameter space should be explored. And one of the messages I want to give you from my talk is that actually I think we can do that. Or I think we can at least, we are starting to do that now. I want to talk roughly, all right, how do we look for this? This is a kind of major topic in particle physics now. How do we try to directly detect the dark matter? There's maybe a lot of possibilities. I want to focus on direct detection experiments. And in particular, let me kind of very roughly divide it into two. On the right side here, let's see if I can get the pointer to work. Not quite. Okay. On the right side of the heavier masses, you should really think of dark matter as being particle-like. Right? If it's a WIMP, there's kind of roughly one WIMP in my fist right now at any given time, one tiny little particle well separated from all the others. And in this case, we've really found that something like particle detectors, like the classic particle detectors that we've built for decades, are best. Of course, here we need to go to very low energy depositions. We need to be able to detect very small amounts of energy deposited, but we're still looking for the dark matter particle to come into your big vat of xenon or whatever, and have a hard, high-angle 2-to-2 scattering off of some xenon atom, either electron or nucleus or whatever. On the other hand, on the left side, when dark matter becomes so light, you should really be, I would argue it's useful to picture it more as a wave or as a coherent field. These little red wiggles are supposed to represent individual dark matter particles whose de Broglie wavelength has become so big, almost macroscopic, that now they are really starting to overlap. And in fact, both when the mass of the dark matter gets light, since we know the local energy density of the dark matter, as the mass gets light, the number density goes way up. And of course, the actual physical size of each dark matter particle becomes very big. So you move roughly locally here in the galaxy, when you're below this 10 eV scale, you move into the high phase space occupancy regime, where dark matter is very heavily overlapped. And you should think of it maybe more like, or it's you. Of course, you can still think of it as particle, wave, same thing, we all know, but it's useful to think of it as a coherent field. And so, all right, my little animation worked. So you should picture, instead of a bunch of individual little bowling balls zipping around, you should picture some more coherent field. I think this, I find it at least very useful to think in this way, to think about the kind of direct detection experiments we want, or to think of new direct detection experiments that we can use to see this kind of dark matter. I would say it's really much more like a gravitational wave detector, right? You could talk, I suppose, about LIGO absorbing individual gravitons or something. That's an accurate thing to say. But it was much more, if you want to think about designing a gravitational wave detector, it was much more useful to think about a coherent gravitational wave coming in and having a coherent action on the detector. Same with these detectors for ultralight dark matter. So I would say very roughly that's kind of how they differ from these detectors for the more heavy particle-like dark matter. This also points to interesting effect, and this is kind of the first thing maybe I wanted to throw out to you to ask if there's kind of any ideas at all, that new ideas we can come up with in cosmology. This lower bound on the mass, somewhere around 10 to the minus 20 eV or so, comes roughly usually from the fact that as the mass becomes so light, the de Broglie wavelength of the dark matter becomes so long that you have some quantum effect of that, some quantum pressure, if you like. It could mess with structure formation. So for example, one simple bound is to say when it becomes lighter than 10 to the minus 22 eV or so, each individual dark matter particle is so big that it won't actually fit in the dwarf galaxies we have seen, right? And so that's clearly ruled out. Or if you try to fit it, of course, you raise its velocity by the uncertainty principle, and then it will escape the dwarf galaxy. But people have also pointed out many other interesting bounds, even better bounds, higher bounds. For example, I think the best current one that I'm aware of comes from thinking about ultra-faint dwarf galaxies. And so this is this paper down here by Dalal and Kravtsov, for example, and some other, that was, I think, the first paper I'm aware of, but some other follow-up papers. Talking about the fact that if you have such large dark matter particles, dark matter waves in the galaxy, so imagine these kind of these red squiggles all over the galaxy interfering with each other, you should think of, you get some wave-like, some optics interference effects, right? And that's my hand-waving way of motivating you to believe that if you looked at what the field looks like in a galaxy, it will have some order 1 overdensities and underdensities spread all over the galaxy on scales of the de Broglie wavelength. So these lumps or nodules or whatever you want to call them are quite big because they're set by the de Broglie wavelength of this very low mass dark matter particle. And they're order 1 over and under densities. Imagine some optics interference pattern, right? You're not surprised that you get effects of the size of the wavelength of the light that you're interfering. It was pointed out that those are very large. If the dark matter mass is so small, those are very large order 1 over densities. Under densities, they carry a lot of mass in them. They're much heavier than a solar mass. And so they will absolutely just gravitationally, with no other interaction at all between dark matter and the standard model, they will absolutely mess with the stellar distributions in ultra-faint dwarfs in ways that we would have seen and are ruled out. And this, as far as to my knowledge, sets the best completely model independent lower bound on the mass of dark matter, somewhere between 10 to the minus 18 and 10 to the minus 19 EV. And that's a very valuable thing to have, right? It says, doesn't matter what model, it doesn't matter how it couples or if it couples at all to the standard model, just interacting purely gravitationally, we've learned something about dark matter. And that also changes what experiments we want to run. We don't have to look in that regime if we know it's ruled out by astrophysics and cosmology. So there's several other bounds people have set, but I just want to throw that out there as an interesting thing to keep in mind if you have ideas about some way that using cosmology, we can set bounds like that or improve those bounds. I think that's very valuable. All right, so very briefly, let me kind of summarize where we are in direct detection, because this has really become, I would say, a major effort in the field of particle physics recently. A lot of people, both on the theory and experimental sides, are thinking a lot about direct detection experiments. So around the 100 GeV, the WIMP scale, of course, we have this long succession. You see here all the many experiments, or some of those many experiments that have been done over the years, doing a tremendous job. This is a plot of the WIMP nucleon scattering cross-section versus the mass of the dark matter, pushing down to some very low cross-sections. And I think if you'd guessed, before all of this, where the WIMP should be, very roughly, we would have expected them to have some coupling to the standard model that put them somewhere in this cross-section range. You can see from the y-axis, that's a lot of orders of magnitude, so I'm being very vague. But it means they're covering very interesting parameter space. And they still have some ways to go. So you can see these dashed lines. We would still like to get down some more orders of magnitude. But they've really also, right now, have covered and are covering a lot of very interesting WIMP parameter space. Maybe a slightly less recognized fact, I said I wanted to look everywhere. Even as you go far to the right, so to far heavier masses, so this is in GeV here up to about a TeV. But even as you go much farther to the right, I think these kind of WIMP experiments, these large tanks of xenon or whatever, are really still the optimal experiment over a wide section of this mass plane in the dark matter. Recently, though, there's been a lot of effort to try to push left to lower masses. And you can see a lot of these curves cut off very sharply at lower masses, because, of course, at that point, the kinetic energy contained in the WIMP is too small. It's below the threshold of these detectors. So one major effort now in particle physics is to push to building detectors with ever smaller thresholds to try to push these limits on dark matter farther to the left. And you can see some of those here. And so, for example, here are two plots on the dark matter nucleon scattering cross-section and the dark matter electron scattering cross-section. And just to point out now, the x-axis is in a different scale. Now it's MeV instead of GeV. And you can see also, you should note, if you compare to the previous slide and this one, that we've moved well left in the mass and also way up in the cross-section. So these are, of course, much stronger cross-sections. We have much smaller active volumes for these kind of detectors. But it is impressive how people have already managed to push fairly deep into this parameter space, and this is really active area of research. People are coming up with new ideas all the time, pushing the experiments further to push farther down the plane to get to ever smaller and smaller cross sections. And so, for example, I'll just point out, one fun idea that came fairly recently was this solar reflected dark matter line here, which is the statement that, well, in this mass range, maybe you thought your dark matter didn't have enough kinetic energy to get over the threshold of a detector, but at such large cross sections, this 10 to the minus 37 instead of 10 to the minus 46 or something, at such large cross sections, there will be some flux that hits the sun, heats up there, still makes it to our detectors here on Earth, and can get over the threshold. So that's a really fun example that you see can also help you push way down in cross section. All right, and then finally, moving left here, in the ultralight dark matter parameter space, you build very different kinds of experiments. So we build things looking for the coherent effects of this whole ultralight dark matter field together. And this is a plot here of, let's say, the coupling of an axion to 2 photons versus the mass. So the coupling, you should think of the coupling as being roughly the square root of the cross section. And all I really want to point out is here, of course, the coupling has to be so weak that you're well below things like supernova bounds and BBN bounds, cosmological bounds. But there are a large number of different possible experiments. So you see a bunch of the names of the experiments on this plot here. And in fact, there's many. I just pulled a random plot from the literature, but there's many more experiments going on. So this is a really active area of research right now. What you can kind of see, you can see in the middle, there are these spikes coming down. Those are microwave cavity experiments looking for axions. On the left, you can see it says lumped element. There's a farther left of that, there would be NMR experiments. To the right, there's a variety of dish and other interesting electromagnetic structures. The takeaway I want to give you from this is that there's a large number of experiments kind of being invented now, being worked on, being built now, that are covering each different piece of this mass parameter space. Especially with the axions, you design an experiment to cover 1 or 2 or something orders of magnitude. But excitingly, we do now have ideas to look in each possible mass range over this very wide range of ultralight dark matter, for example. So the kind of rough conclusion I want to leave you with here is that it's actually a very exciting time in dark matter direct detection. And we really do have ideas that look like we can really start to probe down the plane to ever weaker couplings between the dark matter and the standard model over this very wide range of dark matter masses. And maybe there's a few gaps left that have a lot of us interested in, okay, how do I fill that gap? How do I fill that gap? But roughly stepping back from that, my day-to-day work, I would say it's really an impressive success. People have come up with lots of different ideas. And even the experiments are, sort of prototypes of the experiments, for example, are now being built to really address this very wide range of masses. All right, let me see how much time I have. Very briefly in one slide, I just wanted to mention the hierarchy problem because it has been a kind of major motivation for much of physics beyond the standard model for many decades. And it's roughly the problem of why is the weak scale so much smaller than the Planck scale? We seem to have these large quantum corrections to the weak scale that must somehow, in the standard model, appears very finely tuned, but somehow they must be canceling to 32 digits. So we come out with this low scale of the Higgs that we see. And I would say very roughly, in my maybe controversial trying to cause trouble, I would see sort of roughly 2 classes of solutions. The first would be inject some new physics right at the weak scale to solve the problem. So this would be theories like supersymmetry, large extra dimensions, technicolor, et cetera. The microphysics of all those, of course, are radically different from each other, but in some sense, they're all the same in the sense that they're putting in new physics, new particles right around the weak scale to cure these quantum loops, these quadratic divergences. This would generally require new particles there. I want to point this out, of course, because this can be very relevant to cosmology. This is what makes it a very interesting regime to probe. Also, of course, I have to admit that it has some tension with LHC results, since the LHC has done searches, of course, at the weak scale for many of these kinds of particles, and so far not seen anything. I would say still an interesting idea to explore. Secondly, I'd say there's another class of solutions, which I might call cosmological solutions, where you accept that the parameter is finely tuned in the theory, but there is some dynamical reason that in the history of the universe, it was actually driven to this small value we see. So this would, for example, change the weak scale or the Higgs mass from being some fundamental constant of nature to being some dynamical variable that can change in time. That can create some interesting signatures. And I want to point out this is actually very much like the axion solution to the strong CP problem, very similar to that. Finally, I should say this certainly isn't the only set of possible solutions to the hierarchy problem. For example, people talk about things like anthropics a lot. I put a question mark mainly because, let's say, with even if I buy something like an anthropic and multiverse setup, I still haven't been convinced that any of the arguments I've seen to try to explain the weak tail that way are really lock solid. As in many cases, you have to choose for some reason your landscape only scans a very small number of parameters, and once I add in a few more parameters, there's a way around all the constraints. That's my own personal whatever prejudice. All right. So that was my extremely fast introduction to the hierarchy problem. And I wanted to point out, just as maybe some extra motivation for thinking about this ultralight section of the mass parameter space, these new ultralight particles. I said the cosmological solutions to the hierarchy problem, usually in order to get a time-varying dynamical Higgs mass, you need some light axion-like field. Although for the cosmological constant problem, we've tried for a long time and failed for a long time. So we have I would say no real known working solutions. And it certainly includes all the things I've tried. I personally, my own prejudice is I think the possibilities are similar. Maybe that's just lack of creativity on our part. But you could either introduce new physics right at the scale of the cosmological constant, the dark energy, so right at the milli-eV scale. People have tried that, but that seems very hard because that's an easily probable scale by humanity, by chemistry. You don't need a collider. Or maybe it's some cosmological solution. Maybe it's some scanning, but that would mean the cosmological constant, again, I'm turning it into an dynamical variable, it can change in time. So that obviously has some interesting possible predictions. And would again imply some very light axion-like field. And finally, of course, strong CP problem. I would say the QCD axion is probably the simplest and most beautiful solution. And I would call it similarly a sort of cosmological solution that reduces this nucleon EDM over time during cosmology. All right, so that's just some motivation for thinking about ultralight particles in particular, okay? And in particular in cosmology. That was my lightning fast overview of physics beyond the standard model. And then I wanted to throw a few random thoughts at you, okay? A few random examples that may have some relevance to cosmology. The first is certainly not my work, or I haven't really been talking about my work at all this talk, but due actually, for example, to Dan Green and Dan Bauman and others. If we have these very light particles, if we're interested in looking for those, they could thermalize in the early universe. It depends on the strength of their coupling to the standard model and the reheat temperature, of course. I could come up with coupling so weak and reheat temperature so low that they don't. But I think it's a very generic, very reasonable possibility that we could have that. It's a very valuable signal to look for. And if we do, those, of course, will contribute some amount to n effective, right? We have these new relativistic degrees of freedom. You can see here a plot of the n effective they contribute versus the freeze-out temperature. So if they're in thermal equilibrium at some point, there's some temperature which they freeze out. You can see these blue, green, and purple lines are if I have a new vector, a new fermion, or a new scalar. Roughly the story, of course, if they freeze out very late, you get a very large, already ruled out contribution n effective. But even if they freeze out, what's interesting here, I think the nice point that was made is even if they freeze out at very high, arbitrarily high temperatures, you still have some minimal contribution to n effective, which might even be within the reach of upcoming cosmological measurements. And in particular, I think this pink future target line would assume something coming out of both CMB and surveys. Feel free to correct me if I'm wrong. But so I think that's a really fascinating, really interesting target to hit. And that number 0.027, for example, which would be the lowest number because it's just one single scalar degree of freedom, would be a really interesting number to hit. And is, even not seeing it, that is at the level of, I think, would tell us something interesting. Of course, I'm definitely on the camp of I would love, much prefer discoveries to limits. But I think this is a really generic search for a very wide range of new physics. That's part of why I think it's very useful. I wanted to point out another, sort of random thing I've been interested in personally recently. So now we're getting to maybe more specific and more random ideas. Many dark matter production mechanisms, especially for ultralight fields, although not only, also for things like primordial black holes and so on. Many dark matter production mechanisms have this kind of feature where so you have your standard adiabatic fluctuations from the inflaton at low k. Here's a plot of the power spectrum versus k. But many dark matter production mechanisms have some scale, and they would produce a very strong peak in the isocurvature power spectrum, the dark matter at that scale. And for example, if they're produced causally in the late universe after inflation, you generically would get, okay, you know, at scales larger than that scale, you would wash out that power and it would become homogeneous, but I still have some stochastic fluctuations because it doesn't wash out immediately. And that produces this, you know, fairly universal k-cubed tail on the left here. So I want to argue that it's a, you know, pretty generic thing to look for. This particular plot I stole from a paper of mine on gravitational production of a vector during inflation. That's just one example. I don't want to, you know, sell that one example in particular, just to say there's a lot of examples of this. Actually, for example, the QCD axion itself, let's say post-inflationary QCD axion, the abundance produced after inflation, it has to have a k-cube tail like this because it's, you know, causal processes in the late universe must produce it, and so on, many other examples. So I think this is a really generic thing to look for. And I just wanted to point out, this motivates searches for isocurvature power at ever higher k. So for example, here are current bounds on the power and isocurvature dark matter fluctuations versus k from, you know, Planck's direct search for isocurvature from Lyman alpha. This is stolen from a recent paper of mine where we used this stellar heating effect I told you about earlier in ultrafaint dwarfs. We use that to set a limit on clumps of dark matter also, as well as things like fuzzy dark matter and primordial black holes, just any clumps of any kind of dark matter. And we set this limit here on the isocurvature power spectrum. And if I just use, you know, Keynote to draw a k-cubed line on here, you can see that even though, you know, our limit is way up in power, right? Much, much weaker, you would have said, oh, well, why am I looking for such really high powers, nowhere near 10 to the minus 9 or 10? Still, just by virtue of the math of this k-cubed spectrum, moving to the right in k sets your best limit on k-cubed spectrum. So it sets your best limit on all these microphysical dark matter models, on the production mechanism of dark matter. So this was more to advertise if there are any new ideas. Maybe there's some new idea where someone has a way to move even farther in k, even if it's way up the plane, okay? I just want to motivate that. That's really the takeaway I want to give from this slide, that if you have new ideas to look for dark matter isocurvature farther to the right at higher k, that immediately tells us something valuable. And for example, just to highlight this nice paper of Mustafa and Mehrdad's from a year ago, you could use this k-cube tail to set a limit on all these dark matter produced with all these different kinds of production mechanisms to set a lower limit on its mass. So they had a nice, you know, a fairly modeled generic lower limit on the mass of dark matter, which was moved up some orders of magnitude. So it was a, you know, valuable thing. And if you got to high enough k, you were even, you know, probing the QCD axion. Similarly, there's many other interesting microphysics in dark matter, things like self-interacting dark matter, axion clumps, and so on, that produce these clumps of dark matter that would be interesting to look for. All right, and then maybe my last example, as a sort of random thought that was also given perhaps some more motivation recently by this nice paper by Rajendran and Dan and collaborators. It's a generic question. Can dark matter feel some new long-range force other than gravity that's affecting its dynamics in the universe? That's a generic question I'm just curious to. I'd like to know the answer to. We set a limit. So for example, this plot is from a recent paper of mine. We set a limit on a new, there's different kinds, but we set a limit. This plot is, for example, a limit on a new long-range attractive Yukawa force between dark matter. You can see in the, you know, whatever, milliparsec to gigaparsec range. And the interesting and fascinating thing for me is, so our limit came from looking at coherent scattering of this dark matter in the bullet cluster. So we're aware of, okay, the bullet cluster limits the scattering cross-section of dark matter off itself. But that's been calculated before just for hard dark matter scattering. But if you have this long-range force, large lumps of dark matter will all scatter off each other coherently. And so that hasn't been calculated before. It's the best bound I know of in this regime. And what's fascinating to me, I would say, I can say it since it's my paper, is how bad it is. This alpha parameterizes the strength with respect to gravity. And you can see it's many, you know, even at you know, parsec scales or 100 parsec scales, it's many, many orders of magnitude stronger than gravity. So we don't know that it's really gravity shaping the dark matter on those length scales. I found that fascinating. I also suspect, though, that things like cosmology and structure formation are going to set much stronger limits. So that's you know, let me maybe a challenge to this audience. All right, let me stop there.
Hey, Peter, thanks for the nice talk. Can you go back to the isoculture bound you're showing? I'm wondering, what do you mean by isoculture here? Is that really the matter Paul spectrum in the current universe, or you separate it from the adiabatic fluctuations?
Do we separate it from adiabatic? So, well, let's see. In this paper, we had a different plot just for purely adiabatic fluctuations. So we also can set some limit on the adiabatic fluctuations as well, if that's what you're asking.
Yeah, but I mean,
yes.
Do you show this for primordial Paul spectrum, or it's the current Paul spectrum?
No, this was saying if this was the primordial power
I see.
spectrum. Yeah, exactly.
see.
And that's what, like, so for example, that's what the upper plot there that I stole from this paper on gravitational production of a vector during inflation, that would be the power spectrum of the vector coming out of inflation. Exactly.
I see. And maybe a follow-up question on that, because like, today we hear a lot of talks for large scale ranges, and you're showing this to like 10 to the 4 megaparsec universe. And you're showing some constraints. Maybe in the future we can have some detection. So what do we know for early universe, especially inflation, if we do see something there?
Yeah, maybe I should actually, that could be a question to the whole audience. So one thing I would say is, dark matter production, there are dark matter production mechanisms that can produce this interesting, very large amount of power, isocurvature power.
Right.
But yeah, I love that. I mean, maybe you have another answer to that question as well.
Okay. Right. Thanks.
Peter, this was a really interesting talk, and this is possibly a silly question, but from the point of view of GR, we think of space-time as geometry. So in that sense, it's kind of clear why dark matter should follow gravity. If space-time is really geometric, then everything is following it. But do we actually know for sure that dark matter has to follow quantum mechanics? Because these 10 to the minus 22 EV constraints are, as you said, from basically the de Broglie wavelength of it, assuming it's following the quantum mechanics rules. But like, do we know for sure that dark matter really has to follow those rules?
Great question, of course. I mean, since we actually have no idea what dark matter is, I shouldn't make any strong statements about I know what the rules are for sure, right? I do believe strongly in keeping an open mind until we've proven something for sure. That said, I think people have tried in other contexts to write down models that join both our current understanding of the standard model, which is obviously based on quantum field theory, with something else. So for example, people have tried classical gravity theories that try to, so one way to try to get around the problems we have with quantum gravity would be to try to make gravity, say gravity doesn't follow quantum mechanics. Maybe I'll get in trouble with people who tried that, but I would say I don't think those have succeeded very well. And I think there's some deep problems with trying to marry a quantum mechanical theory to a non-quantum mechanical theory and maybe leave it at that. On the other hand, who knows? Maybe someone comes up with a good idea that we haven't had yet. But certainly all of our thoughts about dark matter are all based on quantum mechanics. All of our, the QCD axion, the WIMP, everything, would be based on quantum mechanics. But yeah, no, it's an interesting question.
Thanks, Peter.
Yeah.
Should I share screen? Hide video. Oh, which one should I disable?
That's fine.
Oh yeah, sorry. Yeah, it's not there.
All right.
Let's cut. Okay.
Telling us about
Yeah, thanks everyone. I was asked to give a summary about these European meetings we've been having over the last couple of years. First thing, we European come in peace. Let me just say that. So I want to thank first all the organizers we had for these two meetings. About 15 to 20 people that are here also participated to these meetings in the past, they helped making this thing a great success. So I want to thank mostly Ennio, Diego, and Marco, who have been helping me organizing these meetings from the beginning, and then all the others which have helped along the way, including Vera, who's also helping organizing this meeting. So the idea of this series of meetings, which wanted to bring together the particle physics and the cosmology community, really started from the bottom up. So me, Diego, and Ennio were just chatting at the Blackboard about something, about new physics, and basically everything that we've written on this Blackboard turned out to be wrong. And this was about February 2020, so within a few weeks, we know that the world changed dramatically because of the pandemic. But what we planted there were the seeds for sort of a number of ideas which we pursued over the years. And I'm happy that, since this completely wrong Blackboard in 2020, now we have arrived here. So as many of you know, we have a 6 weeks long program at the Galileo Galilei Institute approved for 2025. Many of the people in this room endorsed this event, which is really, going to be one opportunity for both communities to join, to be together in the same place and talk about possible new ideas. And I will tell you more in details about what's going on, what's going to happen in the future. But this is a summary of our European workshop so far. So I'm going to put these slides on Indico at some point, and there are links for all of those to the previous meetings. And we have the slides from all the talks. And we have also PDFs of some of the discussion sessions. So the first edition was held at CERN. Then we had ICTP. We're going to do it in Parma in November. And then we have, as I was saying, this GGI event next year. So they're all more or less happening in the same area of Europe. If you're wondering why, main reason is that many of the organizers have very little children. And so we just wanted to have them always close to home in case something happened. And it did happen, indeed, a few times. So, but the real motivation is this one, okay? So this is the abstract that we had for the first edition. And so the idea was really that once we have now routinely done this EFT analysis of lambda CDM, it's time to move on. And we think there is a landscape of possible beyond the standard model models that we need to test with galaxy clustering. And this is an opportunity for both communities to work together. And this is really the goal of these meetings, okay? So this means that it is hard for me to sort of provide a summary because our hope was to get these two communities together. There's a wise man in this room and once said that the best thing of conferences are coffee breaks. So we really designed these meetings around coffee breaks. So really was mostly the interactions rather than the actual talks, which were important for us. But one important point that we sort of stressed from the get-go is that now that we have this FFE, this EFT of large-scale structure, we have a calculable model. And so if we modify it consistently, we can find new physics in precision data. And this is a very different regime than when we look for new physics with astrophysical data. Because there, of course, there are uncertainties about the modeling, whereas here, although maybe the effects are smaller, the precision to which we can calculate the effect is in principle at least arbitrary, okay? But so what is this new physics? And what was discussed? So there are some things which are already, done in the literature since a long time. And those basically pertain dynamics of the universe at high redshift, okay? So everything which happens at redshift greater than 10, more or less, doesn't require any modification of existing large-scale structure codes, okay? So those include things which we heard this morning that we will hear in the talks over the next few days, like interactions of dark matter with baryons, interactions in the dark sector, like the ones that Francis and Gustavo and Martin and others have put forward. Early dark energy, neutrino self-interaction, we hear a lot about those, and also particle physics-inspired solution to H0 and sigma tension. And so one thing that really sort of stressed during this conversation, and this is only an incomplete list of the things that we think are possible to do with large-scale structure data. And so if you have a BSM model in which the dynamics is only affected at very high redshift, and so you can encode the effect in the transfer function, you should just go for it. So just download any code that Misha was saying this morning and run your pipeline and measure these BSM parameters. Okay, so this you can already do. But what was more interesting, at least for us, the organizers of these meetings, is the other regime, in which new physics beyond the standard model happens at low redshift. And this is typically the case if your dark sector is actually dark, so you live in one of these nightmare scenarios in which the visible sector, the standard model, and the dark sector do not talk to each other other than through gravity. And so then in the dark sector, everything can happen, okay? You don't really have constraint that the interactions has to happen at high redshift, otherwise you would have seen it already if it was coupled to the standard model. And so you can really have dynamics in the dark sector at any time, including low redshift. And if you have it at low redshift, and this is, I think, sort of the main message that we were trying to convey over these meetings, you need to modify your AFT treatment of large-scale structure, okay? In the same way, if you want to do BSM physics at high redshift, you have to modify Boltzmann codes. Here, if you want to do new physics at late times, you have to modify these EFT codes, okay? Another example of things that should include the treatment of the EFT, like, for example, you have light but massive relics around the EV. You have ultralight axions. You have late interactions in the dark sector. Peter just mentioned long-range forces. We had a couple of papers, and we'll show you some results. Also, decaying dark matter. If dark matter decays over cosmological timescales, that's also something which would require us to modify the structure of this EFT. And this is important because you see the whole point of this EFT and this large-scale structure business is that we can have a model of the observables from first principle, and there are no large theoretical uncertainties. And so if we try to constrain this model, and this has been done in the literature, and this is my sort of little concern about those analyses, then you really have a large theoretical systematics if you don't modify the EFT codes, okay? So the bounds that exist from large-scale structure on some of these models, I mean, at least in my eye, they have some issue of robustness, okay? And so if you want to modify your EFT for a large-scale structure, you have to go through these 5 stages. And I think this is the reason why this is not routinely done, okay? Those of you, I mean, there is plenty of people in this room that have worked on the Lambda CDM EFT. They know it's painful, but it's kind of the only way. I mean, you know, there's no way to put it, okay? So we do it for the CMB. When we do colliders, we also do it, and so we should also do it now for large-scale structure, okay? And so I can give you a sense why this is hard. Because when you write down the perturbative solution to any order, nth order in perturbation theory, if you have lambda CDM, more or less this is the structure, okay? So you have some nth order growth function here, and then you have some integrals over your loop momenta, some Dirac delta, and then there is a kernel multiplied by n copies of the linear field. Okay, so this is the way we do it in lambda CDM, but this structure already contains a lot of assumptions, okay, which will break down if you have new physics which operates at late times. For example, the ansatz that you can separate space and time doesn't really work if you have a spatial scale in your theory. So if you have ultralight axion, this doesn't work. If you have light massive relics, this doesn't work, okay? So the assumption that we start already is sort of invalid. Then that the nth order growth factor is a simple function, is linear to the n is also not valid. And this is true for all the models of beyond the standard model at late times. And when this is true, it means that the theory has a new time scale. For example, dark matter is decaying. At the same time, if you have new physics, it's very likely that you're modifying the structure of these kernels F, introducing a correction proportional to some new physics parameter epsilon. And the fact that you're modifying the structure of these kernels typically implies that when you do the counter terms of your theory and try to remove all possible UV divergences, you end up having to introduce new terms, okay? So this is why this is complicated. But I want to give you an example which actually sort of answers what Peter was saying before, because at least for long-range forces within some parts of the parameter space, we were able to pull this through. And this was heroic effort from Ennio, Diego, Marco Costas, also in the audience, and then Salvatore Bottaro. And so this is one example, and I think this is sort of could be relevant as a science case for next generation galaxy surveys, because what you see here is the bounds on the strength of this new long-range force. This is what Peter before called alpha, we call it beta. And so this is the strength of this force as a function of the mass over Hubble. And here you see written in terms of the Yukawa parameter in the exponential. And so you can see that we go from the CMB bounds on these new forces in the dark sector, which are of the order of 10 to the minus 2, all the way to 10 to the minus 4, including the large scale structure, okay? And we can go down perturbatively down to 100 kiloparsec, okay? And we cannot extend this treatment to lower masses because we do not have an EFT modeling below those scales. But if we could, and we will eventually one day, We could extend these bounds all the way to the gene scale of this particular light mediator, which means that with something like megamapper, we could have bounds of the order of 10 to the minus 3 on new forces in the dark sector all the way to the parsec, okay, tens of parsecs. And at the same time, we also have works in preparation with fractions. And I will tell you a lot more about this model on Wednesday. Okay, this was just a teaser for those who are leaving earlier. And as an example of what you could do if you really push these EFT programs through. So these are some of the things that came. How much time do I have, Dan? Okay. So these are some of the things that came up during these meetings on top of what I already said. So this is one thing that comes up always when I talk to particle physicists. They say a fluid is not a model. Because in cosmology, always we have a fluid with some W. We've seen, unfortunately, a lot of weird Ws coming up on the archive after the DESI release of year 1 data. And it's really important that you have a Lagrangian before you go macroscopic, okay? And we've seen this in many examples of stabilities and other things. It just happened because you're fine-tuning your parameters at the macroscopic level, but they actually do not correspond to any UV Lagrangian, okay? So this is something important to keep in mind. Another thing that came up is that, okay, we would really like to do this BSM, but modifying large-scale structure code is impossible. I mean, I'm saying it's not easy, but it's borderline impossible. Even, and this is coming from someone who has worked on writing some of these codes. Because the way we solve these kernels using various techniques to the integrals, really to the bone assumes lambda CDM, okay? And lambda CDM is really hard-coded in a lot of the things that we do when we solve these integrals. The particle physicists would like to have something like MatGraph, which is a tool that they have where, you know, they just give the interaction Lagrangian, it computes all the Feynman diagrams, and that's it. This is just never gonna happen. But I think there is a lot of work that we as a cosmology community should do, sort of to go sort of closer to what our colleagues in the particle physics community would like to have, because now our codes are really just too much hard-coded, assuming many things in lambda CDM. Number 3, is there any useful data compression that we can use for new physics? Okay, so this is something that came up multiple times. Again, they would like something which is impossible, like STNU electroweak precision parameters. Not going to happen. But can we do something? Okay, so for sure, BAO is one useful summary statistics, even beyond the standard model. And we have tried to break it multiple times. No one has really succeeded in doing that. So it's really a robust way if you have new physics which affects the position of the BAO to get sort of new constraints. It's not obvious that there is something like this for the shape of the power spectrum. So this is really just open. And related to these issues of summaries and compression is whether there is actually some new observables that we typically don't look at when we think about the lambda CDM model, but it's actually enhanced, for example, if you have new physics. And one thing that comes to mind is, for example, relative velocities between particles, and there is a talk by Caio in a few days, because those are really the things which are small in lambda CDM, but can become large if you have new physics beyond the lambda CDM. Another thing that came up is this sort of interplay between large and small scales. So you have sort of this large scale structure regime in which you have a small signal that you're looking at when in the high precision data, and so you want to have a small theory error compared to very large signals order 1 that you can have at small scales, but maybe there you have large uncertainties. And Misha already mentioned this morning that you know, there is a synergy between the two, for example, with fractions. So when dark matter is 100% warm, for sure, small scales experiment are going to be the way we want to do it. But when the dark matter, the warm dark matter is only a fraction, then we know that the small scales experiment sort of don't have much constraining power, and then the bounds are going to come from cosmology, from large scale cosmology. Okay. So these are the upcoming events. And then I'm going to wrap it up. So we have from November 4th to November 8th in Parma, the 3rd edition of this meeting. Save the date and stay tuned for an invitation, especially those who have contributed in many ways to the first 2 meetings and didn't still manage to give a talk. Looking at you, Ben over there. You'll see an email very soon in your box. And this is instead the 6 weeks program that we have at GGI starting August 25th next year. And so this is going to be a 6 weeks program. And so the first week is going to be a school. Okay, so we think it's important, given that we are trying to bridge into communities, that we have a set of tools which are shared and knowledge which is shared. In particular, there will be classes on cosmology, on EFT and perturbation theory, and how to use these codes to constrain parameters. And then there will be class on model building and BSM in cosmology. Some of the lectures that we have in mind for this school are in this room. They just don't know yet that I will ask them, looking at you, Martin, as well. Then there's going to be the second week, which is really the state of the art. So we will just take it from where we are now, and next year we will see what people have been up to. And the format of this GGI workshop is similar to Aspen. So there is like 1 talk, maybe 2 talks per day, and the rest of the time is just free discussion. Then the third week is going to be sort of planning what needs to be done. And so these are sort of the sets of questions that we will try to answer over the third week. And then the fourth week is kind of this moment where we really want to define one community. And so we want to write a white paper with people from both communities, where we present a range of new science cases for ongoing and future galaxy surveys. Then the fifth week, of course, this is not happening in vacuum. We know that there are already talks about designing of future experiments, and there are other things happening. So there is also interplay with the CMB and other probes, and we will do that. And the last week, the 6th week, is just a more traditional symposium workshop with several talks per day, and everyone is welcome to attend. So save the date, August 25th, October 3rd, 2025. So that's all. We strongly believe that new physics in the dark sector, either at late or early times, should be a primary science case of current and future surveys, way beyond what's currently planned, for example, with things like DESI2 or MegaMapper. And we hope that this series that we're organizing and meetings like this one will help towards achieving this goal. So I hope to see many of you in Parma and Florence over the next few years, and thank you for your attention. It's not really. Yeah, Kyle.
So in your bullet point 4 on the last slide, you have this new science cases for future, bullet point 5. So future experiments, interplay with CMB and other probes, and the white paper. What is your relationship to these future galaxy surveys? Do you have a specific program in mind? Do you have specific number densities in mind? Redshift, like how are you specifying what are the observational components of this program for your white paper?
Right. So I think in order to do that, we will need to sort of define what are the interesting science cases first, and then see what are the tools that we need to develop in order to forecast those, right? So, for example, I think the one that I was showing earlier, this one is, I think, the first forecast for something like Spec 5, where there is a new dynamics in the dark sector in a forecast. So this is one example. And so our idea is that there will be plenty of these by 2025, and then we all converge into the same white paper, and we will discuss things like long range, momentum exchange, and all these other things together. But most of it is still in development, very, very early on phases.
When people develop the models, do they try different assumptions about number densities, or do you think, does it lead to observational parameters, regardless of what the facility is?
Yeah, we could try that. Yeah.
You do
Yeah,
try
I mean,
that?
these forecasts are obtained with the code that we wrote with Noah.
Okay.
It's the same code that you were showing. We just very little tweaks, and you can do some new physics already.
Okay.
I have a question for you. Can you go back to the slide? And this is also sort of maybe for Peter, but the slide where you have the things that particle physicists want, like a fluid is not a model. Yeah. So So in the discussions of non-Gaussianity, we hear a lot about like thresholds, like that aren't firm thresholds. And with the exception of the ineffective threshold that Peter had, I don't see something like, I wish you guys could get to X scale, except for like, maybe there's some new physics below the scale that we can currently measure, but not because that scale is particularly interesting. Is that something that, I mean,
No,
I was at one of the
I think
workshops.
we're
and
very
maybe-
far
okay.
from that
Yeah.
yet. We are still really in the phase that we don't know which part of the parameter space is useful, is interesting, right? And for example, this long range, before there was no bounds, now all of a sudden there's a 10 to minus 4 bounds. And we think there is many areas with there's many low-hanging fruits where this could actually happen. And I think once we have a clear picture, then I think we will say, okay, this is one target, this is another target that we would like to achieve. But
are those targets driven by what you can do or what you think should be there?
no, these are mostly by what you can do, I think. Yeah.
Hey, thanks for the nice talk. I have a very simple question. Can you go back to the mediator mass constraint, the plot? Yeah, this one. I'm wondering why do you mean you cannot extend to higher masses or lower masses?
Well, to lower masses, I could extend, but basically there is no issue. There is no problem because then all the masses are the same. Once you become larger than Hubble today,
Right.
then it's just long range all the time. So
Yeah,
it
yeah,
doesn't
yeah.
matter.
Okay.
To the right, I could extend, but then I would contradict myself because I just sort of claim that you really need to develop this EFT before you do it, right? And so we only did it up to here and we could not extend beyond. And I can tell you why we cannot extend. Because if you extend to smaller scales, so smaller lambda s, so higher masses, then you really have a spatial scale in your theory that you cannot just, put under the rug. And so then this assumption that I can separate the kernels, I cannot do it anymore. And so then I have to sort of start my EFT from scratch. And we haven't done that yet.
Gotcha. Thanks.
So we stopped where we really have an EFT which we can trust.
Yes. All right, so I was asked to talk about dark matter theory, but thank you so much, Peter, for giving me allowing me to take away my first 5 slides. So maybe we can get through this a little early. All right, so let me begin kind of in the middle of things. There we go. So everybody knows cosmic history. I'm not going to go over that, but I do want to separate this idea of how we can go and target dark matter, different dark matter models, different dark matter particle physics, by separating things into 2 different categories, things that affect really the early universe perturbations. And so here you're really altering the initial conditions that you have that are going to seed structure formation. And a completely different type of class is something that is really only happening in the late universe, for instance. So everything looks fine, looks like lambda CDM, and it's not until you get into maybe these high density regions of collapsed halos that you really start probing some sort of dark matter physics. And so these are the 2 different regimes that we're going to discuss for this talk. All right, so starting with the early universe, I want to take a case study because it's 1, the theory that I know best, 2, I have slides for it, and 3, it kind of covers a lot of different aspects of this initial condition issue. So let's just imagine dark matter scattering. So Peter talked a lot about the direct detection
program. And so I like to think about this as direct detection, but with cosmology. So we're looking at the exact same sort of scattering processes between dark matter and standard model particles. It's just happening in the early universe. And so here we have access to electrons, we have access to protons, helium nuclei. So those are our target particles. And the Boltzmann equations are going to demand that we work with this momentum-weighted momentum transfer cross-section. And we're going to be able to parameterize these different types of models that you can have for dark matter into just an amplitude for your cross-section and something that looks like the relative velocity to some power. So I'm going to write down Lagrangians. Manuele said I need Lagrangians, so here are Lagrangians. If you don't like Lagrangians, it's okay. Just know that I can actually have some sort of effective theory, and I can write down things that actually correspond to the parameterization that I am using up there. So these are different types of structures for your interactions that you can think about. And then you can go and plug this into the Boltzmann equation. So in red, I've highlighted the parts of the Boltzmann equations that are not typical. So, you know, you have your density perturbations, but they stay the same, but your velocity divergence perturbations change. And so you introduce what looks like a drag term between your dark matter and baryon fluids. So it's so this interaction causes essentially some drag. You also need to keep track of the temperature of dark matter. So normally the dark matter is assumed to be cold. You don't worry about its temperature whatsoever, but you do need to keep track of it in something like this scenario. So the thing that cosmology really cares about is what's called the momentum transfer rate. So it depends on your cross-section. So the magnitude of your cross-section as well as the particular model that you have in mind that is given by this N. So this N is telling you all your particle physics. Then you also have to worry about the fact that you transfer heat for your temperature evolution equations. I assume Maxwell-Boltzmann distribution. And then some funny issues arise for these cases if you have essentially what is a light mediator. So if you have a very light mediator that corresponds to these negative powers of velocities, you end up with a whole bunch of hypergeometric functions in here. If you're interested in hypergeometric functions, please talk to me. No one has ever taken me up on that. But you know, you could be the first. So the effects of dark matter scattering, and I want to focus here on the CMB because that's one of our earliest probes that we have for cosmology. So this is really ramping up the amount of scattering that you would have. So you have this tiny bit of an enhancement in the first peak due to effective baryon loading. Your peak shift because you're altering the effective sound speed. And the thing that is actually going to dictate the constraint on this type of model is the small scale suppression, okay? So a lot of these dark matter models, not just this, this is the effect that they give. This is the effect that you look for. This is the effect that you can constrain. So we can use that. I have, you know, all my Boltzmann equations coded up and everything, and we can go and search for this in, say, Planck data. We can consider scattering with protons, electrons, helium nuclei, and we can do it all. And we have an enormous range of amount of interaction. Sometimes my mouse is here. At any rate, you can look at the y-axis, which is the cross-section, the magnitude of the scattering cross-section, and it's jumping by many, many orders of magnitude across a really wide range of dark matter masses. So this is just to say that we can do this. I'll put very particular lines into more context in later slides. But this is what we can do with the CMB. Of course, I'm going down to particularly low masses, and you do have to worry about the effects of not only the CMB, but things that came before it. So we do have a handle on BBN. And if you get to low enough masses, dark matter masses, These things are just thermal particles. So this is dark matter that's undergoing dark matter freeze out. And you're going to have energy and entropy transfer from the dark matter to the visible sector as it freezes out. And you're going to alter the Hubble expansion rate if dark matter is light enough such that it's semi-relativistic or relativistic at BBN, right? And so that, for instance, is going to modify how your helium-4 abundance, your predicted abundance under these models look. And so you can consider, say, for instance, both types of effects at the same time, where you have your BBN bound, which is just basically placing a bound on the mass of dark matter, as well as the CMB. And for this particular model that I've shown here, once again, this is the constraints, the plane of cross-section versus mass. And if I were to glue this BBN constraint, if I just did a pure BBN analysis versus a pure CMB analysis, you can see that the combined constraint is slightly different, and you actually lose a little bit of sensitivity because BBN and scattering have some degeneracy. So you're affecting ineffective, you're affecting the helium abundance, and you're affecting this scattering that suppresses, you know, your power spectrum at small scales. All three things affect the damping tail of the CMB. So you end up with a little bit of degeneracy, and you actually lose sensitivity in certain areas. So this is what you get when you combine everything. And so you can't forget about what dark matter is doing even at particularly early times. And so everything from BBN to CMB and downwards, as you go lower in redshift, matter. And so you want to tell a self-consistent story here. So the slightly more relevant observable for this conference is the matter power spectrum. So here I'm showing matter power spectrum as a function of K, and I'm showing you a couple different models with different velocity scalings at the CMB limit. So you can see that you have this strong suppression of the matter power spectrum at moderate values of K, and you see these peaks. And so these are very, very, these are essentially dark acoustic oscillations, a la Francis Yan. And these dark acoustic oscillations come about because dark matter is tightly coupled to your photon baryon fluid in the early universe and undergoing acoustic oscillations with them. So we have data, we have information that go out to larger K. And so we can think about how well can you constrain these types of models with other observations. So here I'm showing you the suppression of linear matter power spectrum in a more sane fashion. It's the matter power spectrum in some sort of modified cosmology case over lambda CDM. Okay. And so the cross-section you can see, or I'm comparing it also to warm dark matter, but the cross-section or the mass of warm dark matter is going to dictate where this cutoff is, right? So you're having a direct handle on the particle physics and the fundamental particle physics of dark matter based on what cutoff you have. And here I'm just wanted to show models that have some substantial dark acoustic oscillations that you really have to worry about and account for if you're going to constrain models like this. All right. So, right, I don't want to focus too hard on my own work in the sense that there's a lot of different models that can give you the same effect. So, no, somebody else try. Oh, hey, nope, but you can't see it. That's interesting. You can kind of see it if you squint. So you have, we have data that go out to certain scales. And so for instance, this line here is for fuzzy dark matter. So we were talking about the lowest mass cases that Peter was discussing before that are really this very, very ultralight dark matter field. You could have interacting dark matter, and here we chose something that had a lot of acoustic oscillations. You could have something like warm dark matter, where it's just the temperature, the velocity dispersion of dark matter that's washing out power at smaller scales. And then eventually you do get some cutoff in a sort of WIMP-like scenario, because WIMPs are going to have some amount of very, very small temperature associated with them. So they do cut off, and you get, something like sub-Earth size halos. But we also have these interesting models that enhance power at very small scales. So the ones that are plotted here are, for instance, an early matter-dominated era. So we don't really know what's happening in cosmology before BBN. And we just assume that it's sort of radiation dominated up until scales that have to do with inflation and reheating. But you don't have to have radiation domination for all time between inflation and BBN. You could have some early matter-dominated phase, and so you start clustering matter earlier on, and that leads to an enhancement of very small scale power in your matter power spectrum. You could also have, it was mentioned, the isocurvature power spectrum. So this is a scenario where you have vector dark matter, and vector dark matter is going to be a source of isocurvature, which produces enhancements at your smaller scales. And then these other two, this axion, this QCD axion misalignment and axion strings, those are two different sort of main production mechanisms for the QCD axion. And depending on which one you choose, you get slightly different enhancements of power. So all of this is to say that there are a lot of different models out there. They give you very different types of either enhancements or suppressions. And so, the smaller the scale, the higher the wave number that we can go, the more beneficial it will be. So for one instance, we can think about some small amount of structure that we have, and that's in the form of Milky Way satellites. And so this is small scale structure that we know is there. We have our classic and Sloan Digital Sky Survey identified dwarfs, but DES has seen a lot more. And we can say, well, for these models that suppress structure, for instance, we can't suppress structure so much that we don't predict that we have subhalos of our own Milky Way. So that's one instance of using galaxy surveys to constrain this. So here are a couple different models. We have warm dark matter, the sort of dark matter baryon scattering model, fuzzy dark matter, and this is the ratio of the matter power spectra in the interacting or modified case over lambda CDM as a function of K. And you have to take this linear matter power spectrum and actually predict what the subhalo abundance is going to be. And so you have some subhalo mass function, and then you have to paint on your galaxies and actually figure out what sort of luminosity function you would expect from this model. And so this is the DES and Pan-STARRS satellites. And this is work led by Ethan, I don't see you, but Ethan, there you go. Ethan Nadler for DES. So he did all this hard work to extract constraints. And for the dark matter scattering case, the amount of constraining power for Milky Way satellites for this particular model that I'm showing here does orders of magnitude better than the CMB. That makes sense. We're going to smaller scales, and all the main effect of this model is at smaller scales. The direct detection bound is what Peter was showing before, and this is assuming that we are scattering with protons. So this is your nuclear recoil direct detection experiments. If you go too far up in cross section, you hit what is called the direct detection ceiling. So there is a point at which these experiments are not going to have sensitivity to dark matter that is, in our local region that experiments are trying to measure, because these dark matter particles would have to traverse the atmosphere, traverse the Earth, and actually make it down to our detectors with some appreciable amount of velocity to create a signal. And so that just doesn't happen. And so these are some estimates for what the direct detection ceiling is. You can also think about scattering with electrons. And I like these particular plots because, as Peter mentioned, the electron scattering program is much newer and hasn't, reached the same level of sensitivity as nuclear recoil experiments go. So at least my CMB bounds actually intersect these direct detection bounds in a legitimate fashion. And depending on what model you're looking at, you can have very different constraining powers as a function of mass. All right. So you can also play this game for warm dark matter and for fuzzy dark matter. And so here we're thinking about specifically sterile neutrino warm dark matter. And we have a variety of bounds that are coming in from X-rays, and we have dark matter overproduction, dark matter underproduction lines here. And we really squeeze, the Milky Way satellites constraints really squeeze out the parameter space, except for this region right here. That's what's left over. If you want to think about ultralight axions in terms of fuzzy dark matter, we decided to have this G-phi gamma coupling that we're going to show all the constraints on. And so DES and pan-stars put some limit on the mass of this particle. So this is a way that you can use, these cutoffs in the matter power spectrum to draw constraints. Okay, so that was all early universe stuff, right? All of the physics is happening in the early universe, the suppression of your density perturbations. And so none of those density perturbations go on to actually collapse and form structures and halos. So instead, we can think about this other scenario where all your physics is happening in the late universe. So you're thinking about what sort of dark matter physics is going to impact halo formation and evolution. And one of the best examples, or one of the best studied cases for this type of dark matter candidate is called self-interacting dark matter. And self-interacting dark matter was sort of conceived to solve these puzzles that arose at small scales. So dark matter is, in terms of lambda CDM, is perfectly consistent for all large-scale structure. But as you get to smaller and smaller scales, there were discrepancies that started arising between your simulations and your observations. And so there are various puzzles that have come and gone. You might have heard of some of them, if not all of them. We have the missing satellites problem, which I crossed out because it's not a problem, the core cusp problem, the too big to fail problem, and the diversity problem. And very quickly to explain what these are, this is the left over here is the density as a function of radius from the center of the halo. And you would anticipate that your dark matter halos would maybe look like an NFW profile, and that's shown in the dotted lines. But that's not all we observe. We definitely do observe cuspy type halo profiles, but we also see halos that have profiles that look isothermal in the center. So these are chord profiles, and so this is the core cusp problem. The diversity problem is one in which you have a lot of different rotation curves. So you have way, way more diversity than what simulations may give you when you have baryonic feedback effects along with your dark matter simulations. And so there's not enough baryonic physics to maybe to account for quite the level of diversity of rotation curves that are seen. So the idea is to attempt to address these various issues with self-interacting dark matter. The target is about a few centimeters squared per gram. For the particle physics people in the room, this is a barn per GeV. These are huge cross-sections, nuclear scale cross-sections. And you definitely need simulations here. This is a continuing conversation between simulators and observers, and you really need to take the time and put in the effort to really disentangle the effects of your baryonic feedback and your new dark matter physics. And so this is something that is this is an ongoing investigation. So I don't do simulations. I like to think I'm much more of an analytic person. So I can take my halo, and I'm going to say that, let's just say it's a self-gravitating fluid. It has spherical symmetry, and it's approximately in hydrostatic equilibrium. And so this is these are the assumptions that go into what's called the gravothermal fluid equations. This was originally used to study globular clusters, but we can use it to study dark matter. And in this scenario, you do have the situation where you do exactly what dark matter self-interactions need to do. They lower the central density of your profile, and they give you constant density cores. And so this is what's being shown in, oh, no, that's, this is what's being shown in this gray dotted line here. This is an initial NFW profile. And very quickly, you get to this light pink line. You lower the central density, you core out that profile. But as you continue letting this halo evolve, it can start growing. So your core starts growing and your core starts shrinking. This is because you have a self-gravitating fluid. It has negative specific heat. So if you just let this thing continue evolving, it's going to undergo a runaway collapse and collapse the core of your halo. And so what you end up with is this very, very high density core that is much cuspier, that looks much cuspier than an NFW profile. And so here, if we're just looking at the time evolution of just the central density, you see that for different cross sections, you can have it so that it bottoms out. You create your low density core, and then it undergoes this runaway process, right? And so the time scale on which this happens matters. For these very moderate cross sections, I mean, 50 and 100 centimeters squared per gram might be a little large, but for the other cross sections, which are fairly moderate, these are cross sections in which, in the lifetime of the universe, your halo, your dark matter halo, is just creating this nice constant density core. All right, so that's what's indicated by the different colored points. This is like, for instance, for the red point, it's what you would get if 0.1 centimeter squared per gram interaction. If you had a halo with that self-interaction, after 13 billion years, you would end up here in the evolution core. So there are ways to speed things up. You can accelerate this core collapse to get these high density profiles. And, is this a bug of your model, or is it actually a feature? And we do observe some systems that have larger central densities than what are expected from lambda CDM. So there are various ways that you can accelerate core collapse. You can have your halo interact with an environment. Maybe your dark matter dissipates energy, and so you lose energy out of your system, or you have some significant baryonic potential that's sitting at the center of your dark matter halo, and so that also helps goes to collapse your core. So these are different ways in which we can think about core collapse, and this very much matters, say, for the Milky Way satellite galaxies, in the sense that these are galaxies that are interacting with our main halo. They are getting tidally stripped. And so if we want to think about SIDM and what effect it has on our observable Milky Way satellites, then we have to think about what their orbital histories are, and how that might be affecting their evolution. All right. So there's a lot of particle physics that goes into this. So there's a lot of model building, and I'm not going to get into the models, but I will say that you have different scales on which you need your physics to be active. So for dwarf galaxies and for low surface brightness spiral galaxies, for these smaller systems, you really need cross sections that are on the level of about a centimeter squared per gram to address the small scale structure issues, but you can't have too much self-interaction in cluster systems. For instance, we have bullet cluster constraints where we have where we can't have the dark matter self-interacting too much, or it wouldn't pass through as we observe it to. Okay. So, so this is a cute little diagram that comes from this white paper about the different ways in which different models of dark matter can impact the halo morphology. And so if you have CDM, you have these NFW cuspy profiles, you have a lot of subhalos. If you invoke fuzzy dark matter, suddenly there's a cutoff scale, right? And you have interference effects. If you have your standard SIDM, which is what I've been talking about, you can get chord profiles. They can also become cuspy because they collapse. And you have a wide range of different central densities to your halos. You could also imagine having some sort of composite dark matter. So maybe dark matter isn't just this simple single particle. And if it dissipates energy, maybe you can have things that flatten out into disks. So instead of having a dark matter halo, you would actually form some sort of dark matter disk. Okay. So I'm almost out of time, so let me surprise you with item number 3, which I didn't put in because I'm mean. And so I just want to give an example of different ways in which both early universe physics and late universe physics actually matters and has some importance. So I want to take a composite dark matter model and just very, very quickly run you through how this affects the early universe and late universe. So you have some situation, let's just say I have dark hydrogen, right? I have an exact copy of the standard model hydrogen sector, and I'm going to have a dark proton, going to have a dark electron, and a dark photon, and it's going to make dark hydrogen. So I have a light mediator. It's going to, this dark photon is going to contribute to ineffective. Your dark radiation is going to cause dark acoustic oscillations. So this is Francis Yan's ethos framework, for instance. And so now you have a cutoff of your matter power spectrum. Your dark matter eventually undergoes, for this case, undergoes some dark recombination process. And so now the physics that was dictating the early universe looks fundamentally different from the physics that's dictating the late universe. And now with a composite object, you can have self-interacting dark matter. And here are all these different ways in which you can have dark matter scattering, and that affects the halo formation. Okay, one other way in which you can think about how early universe and late universe physics interplay with one another. So for instance, we have another probe, cosmological probe, hopefully, and that's with 21 centimeter physics. And so this is showing you the matter power spectrum as a function of K, and this is projections for an edges-like or a Hera-like experiment. And so once again, if let's say we have this dark matter baryon scattering story, right? This dark matter baryon scattering story suppresses structure in the early universe. So there's going to be a suppression in the matter power spectrum. But you can also have the dark matter baryon physics interfere with the astrophysics that you're interested in for your observation. And so for this case, you can have dark matter scattering that comes into sort of contact with the standard model bath late, and that can completely change the 21 centimeter signal that you would expect, because you take these two fluids, you couple them, and suddenly the standard model temperature is much lower than what you would normally expect. So I'm not going to go into any more detail about that. I just want to leave you with this plot of the different ways in which dark matter or cosmology can probe dark matter. And it spans a wide range of scales and a wide range of redshifts. And there are plenty of things here that I did not discuss, but it's very interesting to see how these different probes can interplay. And importantly, these different probes have different systematic errors, right? And so you want to be sure your dark matter story is being told in a self-consistent way. So I would encourage people to not be discouraged if their model seems to be ruled out, because there are, once again, various systematic errors that come into play for any given probe. And I will stop there. Thank you.
Yeah, for the bounds coming from just the number density of dwarf galaxies, is there anything we can do if it's a fraction of dark matter that has the interactions?
Yeah, so if it's a fraction of dark matter, it becomes a lot more difficult, right? Because and I know this is being looked into, but if you have a suppression and it's this clear, nice, clean cutoff, you shouldn't see any structure, right? So if you start playing around with fractions of dark matter that interacts, then only part of the power spectrum gets suppressed, and that's a slightly harder thing to deal with, at least for the abundance counts.
Thanks for the great talk. I have a very simple question for just to understand the physics. Like you mentioned, you have this suppression on matter power spectrum due to dark acoustic oscillations. I'm just trying to understand, like, how do I understand it physically without solving the Boltzmann equations? Why should I expect a suppression at all instead of an enhancement? Is that just like a photon washing out your power, or?
Right. So you have your density perturbations, your dark matter density perturbations, and if you just left them alone, right, the only influence that the photon baryon fluid has is just purely gravitational,
Right.
as baryon acoustic oscillations proceed. But once you introduce the interaction, it's like a drag term, and so there are some, like the baryons that are sloshing back and forth in dark matter potential wells are going to pull some of the dark matter with it. So part of the dark matter starts undergoing acoustic oscillations with the baryon photon fluid.
And that's slowing down the growth of the dark matter.
Yeah, it's destroying the structures of, like, particularly it's very easy to destroy small scale structures in this manner. And so it just washes it out in a very similar way that warm dark matter velocity dispersion washes out scales.
And that's determining the mean free path of the interactions. Okay, gotcha. Thanks.
Well, let's thank him again. Everyone who signed up for dinner, that includes all locals, are free to meander over where we have lunch. We'll see you tomorrow.